Hi, welcome back to es346 Basic Thermodynamics. This is module 5.3 on throttling valve. The section in the textbook is section 5.4 and then the subsection 3. There's two learning objectives in this module. At the end of the module, you'll be able to calculate the temperature change through a throttling valve, and you will also understand the implications of throttling an ideal gas. So first I want to discuss what is a throttling valve. And throttling valve is sort of a general term. And so the book here shows an example of 3 different things that could be classified as a throttling valve. And the way I like to remember throttling valves, it is something where there is a very large change in pressure. So I shouldn't say that it goes up, it's just that it is large. There's a large change in pressure from one side of the valve to the other. So if I had an adjustable valve here that was only slightly open, so there's a very small opening in it, I could accomplish a large pressure drop through here. Another way is to be driving flow through a porous plug where there's not a lot of cross-sectional area in the pore space there. So again, I'll have a large pressure drop through it. And capillary tubes, because they're really small, also have large pressure drops. So think of it as anything that has a large pressure drop. Now, we also talked about turbines, and they have large pressure drops as well. So maybe the other way to think of it is a throttling valve has a large pressure drop and really doesn't do anything else. It doesn't generate any work. It doesn't require any work. All it does is drop the pressure. So that's what a throttling valve is. Let's look at the energy balance for a throttling valve. So I'm going to just kind of schematically draw up a throttling valve here. I've got fluid moving through, and I show this little teeny constriction, so I have a large pressure drop. And let's look at what the energy balance would be across there. Now, one of the things is, since the cross-sectional areas on both sides of the throttling valve are about the same, there's really not much of a change in the velocity. So I can cancel out this kinetic energy term. Kinetic energy entering is about the same as the kinetic energy leaving. Again, it's oriented horizontally, so I can cancel those two potential energy terms as well. As I mentioned, it doesn't generate any work or produce any work, so both of the work terms are 0. And they tend to be pretty small. There's not really much room for heat transfer, so there's really not much Q in or Q out. And there's really not much left in this energy balance. If I look at it, I've got M, H going in equals M, H going out. And clearly the amount of mass that goes in is out, so I can cancel that. And my energy balance is really simple. It just says H in is equal to H out. The enthalpy that goes in is the enthalpy that goes out. And it seems pretty simple, but they're actually pretty interesting devices. So let's go ahead and do an example to kind of illuminate what the implications of this seemingly simple energy balance are. So here's the question. I've got a refrigerant, R134A, and it's throttled. And it says, what is the outlet temperature and quality? So here I'm giving some inlet conditions. I'm given just an outlet pressure, and I'm asked to find what is that temperature. So let me first mention R134A. We haven't really run into this yet. This is a refrigerant. It's another non-ideal material, and there's also a set of tables. So R134A is similar to water in that you have a set of tables and you can look up all the properties for it. It is not ideal. It tends to be a material near its saturation or in mixtures or even as liquids. And so what I want to do is find out what the outlet temperature and quality is. So I'll write down my energy balance, which was really simple. H in is equal to H out. So I have 2 intensive variables here. I have a pressure, and I'm told that it's a saturated liquid. That's what X equals 0 means. It's a saturated liquid. And so I can go ahead and find out the enthalpy that's going in. That's going to be H sub F at 1 megapascal. So that's the enthalpy that goes in. So if I look that up on this is the refrigerant table. So 107.32 is the inlet enthalpy. And I know that that right there is going to be equal to H out. Well, that's not what the problem asks for, though what it asks for is the temperature. So now what I have is I have the value of H. H is 107.32, and I have a pressure. So I have 2 intensive variables where I'm trying to find the temperature. So, well, here's where the key of the throttling valve comes in. I'm at 100 kilopascals, and if I go to, like this over here, at 100 kilopascals, if I look up my values of H sub F, now I'm looking up H of F as 100 kPa here. It is 17.28 kilojoules per kilogram. And if I look at H sub G at that same pressure, that is 234.44 kilojoules per kilogram. In fact, I got the table in the next slide. Let's go ahead and look at where these are coming from. So here's my refrigerant table. I started off at 1,000 kilopascals or 1 megapascal, and I went ahead and looked up what H sub H sub F was. It was a saturated liquid. There's my 107.3, and then I'm going to my 100 kPa table, and I was just looking across it. There's my HF value, and it's my Hg value. So I see 17.3, 234.5, and this 107.34 is between the two. What that means is I have a mixture at the outlet. So let's go back and finish up our problem now. We know that what we have is a mixture, so I can go ahead and solve for x at the outlet. I'm writing this down as conditions 2 now. So x sub 2 is going to be H minus HF over Hg minus HF. And these are, again, all at this outlet of 100 kPa. So we could put those numbers in there. 107.32 minus 17.28 over 234.44 minus 17.28. And that's going to go ahead and give me a quality of 0.415. So that asks for the quality. And as for the temperature, well, what we know the temperature is going to be equal to Tsat. So let's go back onto that table again. Tsat, my temperature is minus 26.37. So equal to minus 26.37 degrees. This is degrees Celsius. Right. Okay. So pretty cold, and that's why these are in parts of refrigerators. So let's go ahead and look a little bit more at where the throttling valve plays a role. And it plays a role in refrigeration. So in the diagram here, I show a classic refrigeration cycle. So here it says expansion valve. It's a throttling valve. The material expands as it goes through it. And there's 4 main components to the refrigerator. If you think to your conventional refrigerator at home, you probably have seen this. This is the condenser. These are the coils in the back of the refrigerator. They tend to be hot, so if heat leaves it, that's what's shown as QH. And then here's the refrigerated space. It's called the evaporator. It's cold, and so heat tends to go into it, from your room into the refrigerator. And then you hear the compressor running every once in a while, and compressors, as we saw in the last module, require work. So those are the 4 components. And if we think about the classic refrigeration cycle here for a minute, so I'm going to go ahead and draw this up as a PV diagram. And I'm doing this for R134A, but the shape of the curve is generally like water or any other material in the phase change. In the classic sense, what I have is at this compressor right over here, and I'll go ahead and call this point 1. The inlet to the compressor tends to be a saturated vapor. That would be point 1. It goes through the compressor, goes to a higher pressure and gets smaller. So I go up to some point, for example, 2 at a much higher pressure. And then what I do is I move through this condenser and I cool off. But I do this all at a constant pressure. So I end up with some point there, which is point 3. And then I've got to get back down to this lower pressure that I'm operating at. And I end up with more or less a saturated liquid. So I shoot down over here to point 4, which I realize I'm in the mixture region. So there's point 4. This is point 2 and point 3 on my diagram, into a lower temperature. So that's what's occurring in the throttling valve. The throttling valve is this step, this important step right here. Now, what's going on between point 4 and 1 again is I'm going to go from this mixture to a saturated vapor. This is where the heat is entering QL. And so if I can know my H values on either side of that, I can find out what is the cooling capacity of my refrigerator. So let's go ahead and do that with the problem that we just went ahead and looked at. And so what we're going to see is that QL is going to be equal to the mass flow rate, and it's going to be on my diagram here, H1 minus H4. So it's going to be off this side and this side. And we just found this value of H here. That's the back side of my expansion valve, the throttling valve. And this value we know is H sub 2. So let's go ahead and do that. So as what the cooling capacity is, I'm given a mass flow rate of 0.02 kilograms per second. Same inlet conditions and outlet conditions. And here the values that we found in the previous problem. Our outlet quality was 0.414. And there was our outlet enthalpy of 107.32. And then this value of Hg, this was at 100 kPa. And so this is what's going to be after the evaporator. So we can go ahead and write our energy balance here to find out what the cooling capacity is. QL is going to be m dot, it's going to be Hg minus H, or like H2 if I'm using that H2 value there. So 0.02 kilograms per second, 234.44 minus 107.32. And do that arithmetic, that's 2.54 kilowatts. So that's the cooling capacity of my refrigerator. Let me just jump back here to this picture again to see. What we did now is we just did an energy balance over this evaporator. We went ahead and said this was H sub G at 100 kilopascal. This right over here was H2, which had a mixture, and it was 0.414. So we used those conditions to determine what our cooling capacity was. All right, one last thing I want to mention are the implications of throttling an ideal gas, because what we've looked at so far in this module is R134A, which was not ideal at all. And so here I've got a throttling valve, and we know from our energy balance that H in is equal to H out. And the other thing we know for an ideal gas is that H is equal to Cp times temperature. Enthalpy is only a function of temperature. So if I put that in there, I find Cp Tn equals Cp T out. And so if these heat capacities are more or less the same, and they tend to be, they don't change a whole lot, I just find out that Tn is equal to T out. Which just tells me there's no temperature change through a throttling valve with an ideal gas, which is the exact opposite of what we saw with non-ideal. In fact, the point of the throttling valve was in order to get a temperature drop through it. So it's an important concept to remember. If you throttle an ideal gas, the temperature doesn't change. And if you want a temperature change, you need to throttle something that's not ideal.